Hello, my name is Valentin Batteiger. I'm responsible for the research area Future Aviation Fuels at Bauhaus Luftfahrt. And today I will give a presentation on synthetic jet fuels and a long journey to climate neutrality together with my colleague Antoine Habersetzer here at the Bauhaus Luftfahrt booth at ILA in Berlin. Okay, so talking about climate impact of aviation. So we have two major contributions. One is the typical greenhouse gas emissions that you also see in other sectors, dominated by CO2. And obviously, this is where we have an essential impact with alternative aviation fuels. And different scenarios exist on how efficiencies will evolve, how traffic volumes will evolve. In any of these scenarios, we need substantial quantities of aviation fuels to achieve climate neutrality. In addition, we have the so-called non-CO2 climate impact. Again, we can do something with the fuels. Again, we can do something with technology improvements, and in both cases, we can also do something with operational measures, but from now on, we will mainly focus on the greenhouse gas emission and CO2 factors in these presentations. The next slide shows a little bit the different technological options that we have at aircraft level in aviation, and clearly electric aviation can do something, but only at a very short flight distances. And this has a certain traffic volume, but if you convert it into the fuel volumes that you can actually substitute by for instance, battery electric aircraft, it's a small share. And for the bulk share of the energy demand of aviation, we certainly need a liquid fuel also in the future. So this liquid fuel could be liquid hydrogen, and we do a lot of research on hydrogen aviation at Bauhaus Luftfahrt, but the baseline case to reduce the climate impact of aviation to zero until 2050 is a synthetic kerosene that we will certainly need to do something on CO2 emission in the short and medium term future. Here I want to set a little bit the scale to show you what we are talking about. So what is compared here is in the middle the aviation fuel demand of about 300 billion tons in comparison to a bigger bar, which is middle distillates. So this is dominated for diesel consumption, mainly for road transportation, and then you see the world refinery output. So aviation is only 8% aviation fuel of the world refinery output. Still, it is very big if you compare, for instance, to the current biodiesel production, or if you compare it to the potential. So this is really a potential that we could serve, for instance, with a waste-based fuel based on waste cooking oil or something like this. Still, if you transfer this into market opportunity, even this small used cooking oil potential is a 10 billion euro market. So it's really big scale that we need to go there. And as we need to go big scale, we need to develop solutions that are then also available at large scale, large volumes, large quantities. And this is where synthetic fuel production comes in from renewable energy, so mainly from solar power, from wind power. We call it power to liquids, also called e-fuels, e-kerosene. This is the typical things that many people talk here also about ILA. Recently, we had a report, Power to Liquids, Scalable Sustainable Fuel Solution, Fuel Supply Perspective for Aviation. So this was together with Ludwig Bölkow Systemtechnik and Umweltbundesamt, a lot of detail in here. What the chart shows is the main motivation to go to these synthetic fuel options. It's the scalability. So we can simply produce a much greater volume of power to liquid fuels from solar and wind energy from the same area compared to a biofuel. On the other hand, the challenge that we face with the synthetic fuels is clearly the cost. So synthetic fuel production is costly. It will also remain costly in the future. You see here some estimates where we can go from today maybe to the future with technology improvements, and what is a main factor also with lower costs for renewable electricity, with lower cost factors that we have to assume for the electrolysis section. But also in the future, what we expect is that the provision of green hydrogen is the major cost driver for these synthetic fuels. So electricity in first place, and then also the electrolyzer. And this is why it probably will also never get a really cheap solution, because this is just what we need as an import for these things. Other things are also important, like CO2 capture. Here we already assume quite an aggressive technology advancement for direct air capture in the future, and also synthesis and conversion units are not yet there where you see it today, so certainly there's also some development effort needed. Then, talking about this big piece here, the electricity supply, this is also something which is dominating the sustainability of these power-to-liquid fuels. And when you make a break-even estimate, so you convert electricity into a fuel, this 125 gram per kilowatt hour of electricity is your boundary where you begin to reduce emissions compared to fossil kerosene. And what you see here, when you have a grid, as we have it in Germany at the moment, still with a lot of coal-fired power plants, gas-fired power plants online, then it's not sustainable to produce such a power-to-liquid fuel from the grid. In some countries, even in Europe, we can already go to deep reduction. We can also go to a reduction smaller than 38 gram per kilowatt hour, what we need to fulfill the requirement of the Renewable Energy Directive. But when we are in countries like Germany, we certainly need to go to wind power, for instance, to achieve this value. So we cannot use the grid at the moment. And then another thing is the scale. So we will need a lot of renewable electricity. So this is available when you compare it to the potential, but still it's on the order of magnitude to the current electricity consumption that we have in Germany. So this is why we expect that it makes sense to produce a certain share of power-to-liquid fuels in Germany nationally, but the bulk part will probably come from imports from countries with more suitable renewable energy potentials. So my last slide before I hand over to Antoine Habersetzer is our fuel land map. So this is way too much detail to explain it here, but what we essentially do is we are looking at all the different alternative fuel options that we have at hand. So biofuels, first generation biofuels from agricultural products like sugars, starch, oil plants. And here we certainly have a sustainability problem. So they usually don't even fulfill the minimum requirements of the European Renewable Energy Directive. So we don't want to use them. Then what you see more to the down left side are the advanced biofuels options, and they are complex. So they should certainly be developed. Many of them are not yet there, but this is another handle that we have here. And the bubbles indicate a little bit where we can go with pathways like power-to-liquid pathways, like solar-to-liquid pathways, which are certainly on the expensive side for today, but have the advantage that we can really bring them to the scale and to the volumes of fuel that will be demanded in the future. What you also see a little bit as a smaller bubble down here is the liquid hydrogen. Clearly, liquid hydrogen has a cost advantage at the location of production, simply because the pathway from electrolysis to liquid hydrogen is much more efficient and shorter than when we go into the fuel synthesis. And with this slide, I hand over to my colleague Antoine Habersetzer.
Thank you so much, Valentin, and also from my side, a warm welcome here at the booth at ILA and also online. My name is Antoine Habersetzer, and I would like to now switch the perspective. While Valentin gave us some super interesting insights on the PTL fuels and the details behind the production, I would like to take a step back and look at the overarching picture. So which role can SAF and PTL play on this long journey to a sustainable and fossil-free aviation? And as you all know, we have a lot of possibilities in aviation to reduce emission intensity of flying. We have technologies at the aircraft level, we have operational improvements, we have radical technologies, we have new energy carriers, and of course, sustainable aviation fuels. And you will quickly see that this picture becomes quite complex. And especially when we look at longer time frames, uncertainties rise. And so it's really a complex task to think of, well, how might aviation develop and what are the building blocks that are important to get to a fossil-free aviation? And one quite powerful tool to have a better understanding how the future might look like is scenario modeling. So really trying to figure out what are possible futures and how do the decisions that industry and policymaking takes today will shape the future of the industry. And what already Valentin also said, well, kind of for most of the scenarios that we know and that are discussed today in the industry, we know that SAF will play a key role. But what role exactly? And this is what we at Bauhaus try to catch with our integrated scenario tool. So really trying to understand how do the different building blocks that shape how aviation is developing, how do they interplay, and how can we better understand how the decisions that we take today, the investments that we take over the next years, will in the end influence where we get. So we are really convinced that scenario modeling is a powerful tool to support decision making, both in the policy sphere and in the industry. So what could that look like? Let's have a deeper dive into what scenario modeling can actually tell us. What you see on the right-hand side is probably a graph that you have already seen here and there. So the typical way of showing how can aviation in the long term get to a sustainable and fossil-free way of operations. So the top line shows you how would the emissions here, the CO2 emissions, evolve over time if we don't do anything, if we simply have a direct relationship between air traffic growth and emissions. And then the different colors show you what the individual options and mitigation possibilities that we have, how can they contribute of reducing these emissions. And what you instantly see, the dark blue area is what SAF is contributing to getting aviation fossil-free. On the left-hand side, you see this as a more condensed way. So the overall contribution, what SAF can bring of making aviation sustainable and fossil-free. But what does that mean? So what should we have to do now to get to that picture? We really have to think about ramping up SAF then in the long term. And let's just assume, and that's what you see on the right-hand side, let's just assume we have an exponential growth. So a typical market uptake of SAF technology. Well, then you will quickly realize that we have to add a lot of capacity in the long term. That's what you see on the bottom graph here. So this is what we have to add as production capacity every year to get to 100% SAF in 2050. And that's roughly 20% capacity growth every year. And what you will see then, especially in the 2040s, this is quite challenging. And honestly, looking a bit frightening. But I have two good news for you on that case. First of all, look at the 2020s and the early 2030s. you see that there the growth of the capacity is pretty moderate. So there we really have a lever by policy and by industry commitment to increase the ramp up in the early stage of SAF production. And the second good news is we know from other energy technologies that once the first market uptake is realized, so typically we are talking about 5 to 10% market share, then we see the self-reinforcing market dynamics really kicking in. And that's what we see with renewable electricity, for instance, today. The capacity addition today regularly exceeds what was expected. So this is where we need to get. Ramp up SAF quickly so that in the end we are kind of reducing the tension. And the second message I have for you is, well, the quality of SAF matter. And I'm talking about the sustainability quality. What you see on the top here is what would happen if we have an average CO2 emission reduction of 75% of our SAF, which is already quite challenging, which is, for today's standards, a quite good SAF. But you see with this gray area below that we still have an emission gap that we cannot address, that we have to offset. While on the bottom, if we assume that the SAF is 95% reducing CO2 emissions on its life cycle basis, then we are almost getting rid of the emission overshoot, right? So really the quality of SAF matters in the end when we talk about sustainability. Let me quickly wrap up what Valentin and myself were exposing here. So first of all, if we want to get a sustainable and carbon-free aviation sector, we need to put all the different building blocks that we have together. That's efficient aircraft, that's good operational procedures, and that is sustainable energy carriers. We will need large quantities of sustainable aviation fuels, and that's why we need to ramp them up fast so that the self-reinforcing market dynamics and cost reductions are kicking in as soon as possible. There, then again, the quality of the SAF is very important. We need to have good SAF in the end because, well, if we end up with an emission overshoot, then nobody really wins. What we really want to have is a sustainable, carbon-free, and efficient aviation sector. And finally, in all these discussions about SAF, hydrogen can have an interesting role. We can play out synergies here, but this really depends on technology development, fleet overhaul. But that's a talk for another day. Thank you very much for your attention, and we are happy to take your questions wherever they are. Thank you very much. Sehr gut.